Well, let me first. There are actually two talks in this. There's the first. Can everyone hear me? Or so what I like to do is you can great. Okay, I like to first give the polite talk where I talk about how great we are, and then I like to give the real talk where I talk about how stupid we are, and that's the one where you learn the most stuff. So, but first, just to give you a bit of context, I'd like to fly this little helicopter. This is a hacked E-flite Blade MCX. This is the end result of a $1.5 million DARPA project. Thank you, all of you wonderful taxpayers. I hope you think this is money well spent. So let me just, pardon me?
Internet, well spent.
Internet is very well spent. Okay, so there we are.
Cool.
And that's it. Basically, this is our show and tell thing. You plug it in. It takes a visual snapshot of the world, and you can see 8 little cameras on it, and basically all it's doing is just trying to hold a position using purely visual information. It's not even using an IMU to do that. And if I move my hands around it, you can see that it'll actually respond a bit. Hey, respond, I'm giving a presentation. There you go. As it's actually tracking my hands, because as the world moves around it, it thinks the world is moving. And this is sort of an insect-inspired behavior. If any of you have gone hiking in the woods and you notice insects flying near vegetation and a gust of wind comes and the plants move, the insect will hover near it and follow it. It's pretty much the same concept. You could take this and bop it around. It'll go back to where it is. If you perturb it, listen, it gets mad. It doesn't like that. But it's a very simple demonstration. Let me let's have a little fun here. I have to do this right now. Get one going. And we'll get a second one going. There we are.
That's cool.
It's fun. So I'll fly it more later on afterwards, and some of you can come up and take a look at it if you want, play with it yourself. Where's the other one? There it is. Okay. One thing about robotics is that when things work, it's actually kind of boring. When things are barely working, that's when it looks the most interesting. I gave a talk earlier today, and something happened. It ended up flying toward the ceiling, and it spent the whole battery charge about a foot away from the ceiling. I'd never had that happen before, but it was pretty funny because I was trying to give the talk while it was hovering. Okay, we can play with this some more later on afterwards if you like.
Is there a communication option, or is it completely on its own?
There is a communication option, not for this firmware, but we do have a version where you have Control 6 and you can fly it around, and you adjust the set point, and you can basically, what's cool is you can fly it and make it move, and you let go of the sticks, and it stays there. So we have that option. We've also flown it in the dark. Here's a question. This is a quiz. This is an earlier version of this, and all this one does is controls its yaw, its angle. Control is on, control is off, control is back on. Okay, but basically it spins and then it stops. And so my question for you, and you can answer me later on, is how many megapixels did I use to do that? Whoa, it crashed. Okay.
I thought Max didn't crash.
That's what I thought too. That's what I thought too. Okay.
It was too boring when it worked.
I know. Okay. So what I'm going to do once this thing loads up is I'll tell you a little bit about how this works. Who here does not know what optical flow is? Okay. So the concept of how this thing works is hello. I'm seeing a spinning beach ball thing. Okay, there we go.
You okay?
Yeah, I think so. I think so. Let me.
How much was the DARPA grant again?
This is a totally different presentation. $1.5 million is how much we spent on that, and that includes a lot of messing up and going down bad paths and making mistakes and so forth. We have a lot about that. So basically, I can talk at length about that. Optical flow is the, if you imagine yourself an insect, is the apparent visual motion that you experience when you're moving through the world. So you're traveling forward, you look down, the ground appears to be moving backwards. You travel down a tunnel, the walls appear to be moving backwards. And you can tell where you are within the tunnel by how fast the walls appear to be moving. If the right wall is moving fast, that means you're probably closer to the right wall. So you can equalize the optical flows and keep yourself in the center of the tunnel. Or in this case, you can just keep the visual motion 0, and just by doing that, you're able to hover in place. And what's interesting about this, well, biologists have discovered what you can think of as stratagems, basically heuristics, that take visual motion cues and map those onto controlled responses, like to hover in place, keep the visual motion 0. To avoid an object, turn away from regions of the visual field that have a rapid expansion. You know, if you see something rapidly expanding, you're about ready to bump into it. And what's interesting about those stratagems is that they basically map a visual pattern directly onto a response. Usually in robotics, you have sensors and you create some sort of state and you control the state. In this case, they're actually controlling the visual field, if that makes any sense. This is actually heretical in robotics, perhaps. But the approach that we use, I like to use what we call a vertically integrated approach. And I think this is actually the reason we were able to do what we did. And what I mean is, here's basically the signal processing pathway. You have optics that takes light, focuses an image on an image sensor chip, hardware, software that processes it. We have actually worked on all these different layers. And an interesting thing happens when you design the optics, design the chips, design the hardware, and so forth. You can control the interface between the different layers rather than being constrained to some arbitrary standard. You can decide what's important to keep it, and this is most important. You can decide what's not important and get rid of it. And that methodology is really why we've been able to do what we did.
Did you design your own chip?
We actually did design our own chips. I have some silicon right up here, if you're curious. I mean, some things we've done in the past, we've actually looked at putting analog circuits on the chip. So a chip would have pixel circuits and then analog circuits to partially process the image. So then what comes off of the chip is a pre-processed image that you can then use a simpler processor to control. So we played with tricks like that. But what I'm going to do now is basically just tell you how this system works. What I'm going to do is just go to this slide. So there are basically 4 different visual modes that the sensor ring is picking up. There's one that corresponds to yaw. When the helicopter is turning to the right, the whole world appears to be moving to the left. There's one corresponding to heave. If the helicopter is rising, the whole world appears to be lowering in all directions. And if you're drifting in the x or the y directions, you can think of the optical flow as forming basically a sinusoid. So if I'm traveling forward, the optical flow is 0 in front, it's 0 behind me, and it gets bigger to the side, goes back to 0, and then it gets bigger in the opposite direction and goes back to 0. That's a sine wave. And so what we can do is basically compute, sorry for the math, but you can compute basically a dot product of the optical flow with that fundamental pattern. And that tells you if you're yawing, if you're heaving, or if you're drifting. And this concept is really, this is actually loosely based upon some studies performed on insects, on the visual systems of insects. There are actually neurons in the fly's brain that respond directly to visual patterns like that. It's pretty fascinating how the scientists figured that out. They actually mounted a fly into a little assembly, probed it with probes, and then at each part of the visual field had a circle move around, or a little spot move around, and they recorded when the neuron fired. And based upon that, they were able to figure out sort of a tuning pattern of that neuron. And some tuning patterns corresponded to yaw, some corresponded to heave, and so forth. So it's really interesting that the visual system of the fly is tuned to pick out things pretty much like that. And all we did was really put this into hardware. The nice thing about these 4 modes is that they actually nicely map onto the 4 modes of a E-flite blade MCX. And I mean, who here knows how this thing flies? Or who? Okay. It's a very simple control. You have 2 blades spinning the opposite direction. When one blade spins faster than the other, the helicopter spins. When both blades spin the same rate, say increase at the same rate, the helicopter rises. It's pretty simple. And you have a little swash plate that's used to make it drift in the sideways directions. I can go in more detail later on or afterwards if you want. It's a pretty simple thing. So all we do is we just took a simple PID control loop and mapped it onto the control of the helicopter. So if the sensors picked out that it was yawing, we just took the blade that made it spin in the opposite direction, made it spin faster, and the helicopter corrected itself. Very, very simple. As far as the details, we have 8 cameras mounted on a ring. That's this little ring right here. Each of these blue squares is an actual camera. And each camera has a chip. I call it the Faria chip. It's actually, I actually have the chip up there to see. So basically it's a 64 by 64 pixel array that goes to a 64 by 64 capacitor array. You can think of the capacitor array as an analog frame buffer. So you just take a snapshot that way and then use switching circuits to smooth the image or do various operations. In the case of this helicopter, we just take the 64 by 64 and bin it down to 2 separate images, basically a 32 by 1 and a 1 by 32. So the horizontal stripes measure vertical visual motion and vice versa. So really, from each image sensor, we're only getting 64 pixels. So that means that this thing is hovering using only 512 pixels. You know, we all have, many of us have iPhones that have our 8 megapixel camera. You don't need a megapixel to do interesting things. Fruit flies can live their whole life with 400 pixels, and dragonflies, I think it's around 10,000 pixels. And this is 512. So who can guess how many pixels that, remember that yaw helicopter? How many pixels were needed to do that? Who can guess?
8.
That's right. You read it from the website?
No, you have 8 cameras and you get.
It doesn't start to degrade.
Gosh, that's a good question. There's a whole field called visual ecology. I'm not making this up, where scientists study, what is actually out there in the visual field that lets insects do or animals do what they do. What's interesting is that there's actually a somewhat of a 1 over F type of spectral distribution. So if you look out there, there are a lot of very fine features, but then there are also, say, you think of as longer wavelength features. So not in all cases, but in a surprisingly large number of cases, there's pretty much always something that you can lock onto. Not in all cases, though. So there are failure modes. There are cases where this won't work. So I don't know if that answers your question. But another thing, of course, is actually in terms of resolution. And obviously, if you're trying to pick out a target that's a mile away, you need more than 8 pixels to do that. So you have to keep in mind what it is, what the application is that you're trying to do before deciding how many pixels you need.
Is there built-in redundancy if you lose some pixels?
Well, in this case, the redundancy is not so much by built-in pixels, but just by the fact that it's responding to a whole visual field. So if there's nothing over there, elsewhere there is something. And you notice that I can walk near it, and it didn't really move much, and that's because the noise or the noise signal that I'm giving it by moving is averaged out by everything else around it. It's another trick that insects use is that they actually see omnidirectional.
So basically, all you're detecting with your 8 pixels in each camera, along, let's say, the horizontal axis, is movement.
Correct.
Nothing else. I mean,
That's it.
Not trying to identify features or anything.
That's it.
There's enough to say that there's movement or not movement. And
Artificial stupidity is what I call it.
Pardon me?
Artificial stupidity. But just to give you a sense of what you can do using vertical integration, and this is really getting esoteric, or not esoteric, just very basic. We came up with a nice interface that allows a single processor to control a number of chips. A very simple interface, but we even chose the locations of the bonding pads, the signals on the bonding pads, so they would line up with a circuit board that allows us to mount that chip directly on. I mean, that's not rocket science. That's not difficult to do. But even something that simple, if you can control both the image sensor chip and the circuit board, it gives you that flexibility. You can start playing games like that. And I just have a whole list of it. I mean, you've already seen this fly here, so I just want to show you one thing three little quick videos. This is about 3 years ago, actually. This is a larger room at the University of Maryland, and so we actually flew it there. It was actually fun because grad students would walk by and, what is this thing? A large room, and the same day in a small closet. So this is the same helicopter, same control rules, same control constants, and it was able to work in both environments. In other words, this thing works better than I thought it would. I did not think it would work that well. We even added on the LEDs and had it fly at night. And this was our last demonstration we did for our sponsors at DARPA. They were really happy. We flew it around and let it go, and it just sort of stayed there. This one we had to use 1,000 pixels.
Could it see in the darkness, or was it just sort of?
By itself, no. By itself, no.
Can it see infrared? If you put infrared LEDs and stuff.
Oh yeah, it could see near infrared. We chose to use visible because I mean, to be frank, it's actually pretty difficult to do an experiment like this because you have to close everything down, and if you use near infrared, you wouldn't be able to see it, so you wouldn't know if it's working.
You'd hear it bumping into things.
You'd hear it bumping into things. That's a very inefficient way to do things.
So what's it seeing in this environment?
And it's the same thing. It's measuring optical flow. So basically, in this case, we're using just 4 sensors. And one LED lights up the visual area for one sensor. And it's just basically looking at that area, measuring the optical flow, and computing those 4 coefficients.
So it's using the light it generates.
Yes.
So it wouldn't work in a big room, for example.
I'm sorry?
It wouldn't then work in a big room where
No, it would not work in a big room, and that's something that we have plans to tackle. So I think here, each pixel is getting maybe around between 10,000 and 100,000 photons per second, which is quite a lot.
Would we get a room full of mirrors?
I doubt it. If there were mirrors in the room, it probably would work. If the room was nothing but mirrors, that would be very interesting. That would be really interesting. You know, I think it would handle y'all okay, but I think you'd have some problems in general. That would be fun to try. You know, earlier today, actually, we tried. It was hovering over a table, and we all started walking around the table, and it started rotating, and it you know, so it's not obviously as far from perfect. So anyway, this is the end of the polite talk. So now let's get to some of the real stories. And this goes way back a long time ago. This is old. This is from 10 years ago. This is back when we first started. Before we knew what FAA was, before we knew what ITAR was, before we knew what... well, we actually did some flight tests at a park in Washington, D.C., which apparently was on the flight path of Marine One between Andrews Air Force Base and the White House. And after one flight, we saw a helicopter overhead, and 10 minutes later, a big car and a very big, menacing-looking person told me to go elsewhere. Basically to another park in D.C., which is funny. And in the other park, the police would come and watch us. It was just, you know, they wanted to take a break. Anyway, sorry, I digress. So one of the earliest things that we were trying to do was to make an airplane avoid trees. We start out with this. A very simple demonstration, just a single optical flow sensor looking down. As the airplane flew forward as basically a foam wingow, it would use a proportional control loop to pull its height. If the optical flow in the downward direction was too much, increase your throttle or increase your elevator, go up, and vice versa. Very, very simple. And around that time, this is when some guy named Donald Rumsfeld took up a position and brought in Tony Tether, and he was very much interested in metrics. Tony Tether was the original, was the director of DARPA at the time, and he was very much interested in trying to get people to do something, you know, take measurements to make sure people are actually accomplishing anything. And so what happened is there was this overwhelming force to measure everything. And so we had to not just fly it, but actually take measurements to show it was working. And this is one of our first attempts at avoiding a tree. There's the airplane, and you see a tree, and that's kind of what happened. No, but look, we have metrics. See, if you look at the graph, you see that the optical flow goes up, and the rudder starts to turn before the gyro detects the collision. So it worked. No, but anyway, since we were trying to take ideas from biology, I thought about this. This took about 2 years. This is a flight path of a fruit fly. This is done by Michael Dickinson, a professor. He's at Caltech. It's an arena about this large. And what a fruit fly would do is make a straight line, make a sharp turn, make a straight line, fly this type of path, fly straight and make a turn. And what they figured out was that the turns were very, very tight. And we realized, wait a second, the reason fruit flies are able to maneuver is that they can turn on a dime. Our airplane was loaded down. So we actually defined a measurement, a metric. I call it D over R. D is the typical size of an object or an opening. R is your turning radius. It's kind of a first order measure of how maneuverable your airplane is. And D over R, so a higher D over R would be an easier environment because everything is big compared to how well you can maneuver. So insects were flying in a D over R of maybe 10, and we were flying in maybe 1. That's why it didn't work. Our airplane was too heavy. It was loaded down. So what did we do? We built a new airplane. So our program manager said, Jeff, all we want to do, forget the metrics, all we want to do is to see the airplane turn away and avoid trees. I said, why didn't you tell me that in the first place? So what we did is we took all that extra crap. We designed this very ugly airplane. It has basically it has a propeller and a rudder and things that pass for wings. It was an airplane that was designed to be more maneuverable. So we got that problem to work, and the electronics, we didn't change very much, except stripped out a lot of weight. And here's a video. This is when it was barely working. It looks really cool because it kind of steers away from the trees. It gets confused a bit, and then goes back to the trees and escapes. I didn't quite have faith in it yet. And what happens? Does this show go down? Oh yeah, because we actually learned that if you didn't have an automatic cutoff, it would actually fly away.
One quick question. So
Yeah.
you mentioned program manager. So is this done through SBIRs, or how did you guys?
That was not done with an SBIR. This helicopter was done with an SBIR. So we've done some work with SBIRs.
So what was your initial funding? Was it self-started, or how did you guys get going?
Oh gosh, what happened is at DARPA, basically the program managers have consultants called SETA, S-E-T-A, Science and Engineering Technical Advisor. Basically a consultant to come in and help them manage the projects. Subject matter experts is another word for it. And so I took a consulting gig for one of those, and rather than pay myself, I hired back some high school students that I had before when I was at the Naval Research Lab, and we basically replicated work we had done earlier and improved upon it. And so the program manager said, hey, why don't we give you more money to do some stuff? So it's pretty much like that. So I was living very lean for a while. But the takeaway lesson here is that the way we were able to get the system to work, even though it's a visual system, the way we were able to get it to work was not to make the visual system better, but to make the airplane more maneuverable.
So if you had focused more on the electronics, the optics, how much more would the weight of the helicopter have gone up rather than if you had focused instead on the insect behavior type of thing?
It becomes a death spiral. I don't know, because we haven't gone down it. We started going down a direction that wasn't feasible, so we stopped. No, it could get very heavy very fast, I think. I don't even know. I don't even know how to answer that. I would dare say anywhere from a couple hundred grams to a kilogram or more if you're using, say, purely off-the-shelf cameras.
You mentioned that the program manager had suddenly said, all we want you to do is nest trees.
Mm-hmm.
Why didn't you know that before Was there a different objective? Or was it just
Well, I think what happened is that before the emphasis was on achieving metrics and getting data,
okay?
and what happens is that if you're several weeks from a deadline, sometimes you get very creative. If you're on to money, sometimes you get very creative. Because what happens is you just sort of cut to the chase and clear out all the other unnecessary stuff, and that's pretty much what happened in his case. Because he realized, okay, fine, we don't have the metrics, but if we have it turning away from tree, that's the 80% we want. That's the answer, and that has come up over and over again. Feature creep. I hate feature creep. We also come to feature creep. So,
Before you go to the next, on that,
yeah,
you said you decreased R, the turning radius,
right.
but you also could have increased D. And at the moment you had your visual flow aimed down at the ground.
Mm-hmm.
Right? It strikes me that either compromise the 45 degrees or having a second camera that was forward facing,
Mm-hmm.
looking flow where something's approaching it, would have increased D. Is that correct? Am I understanding it properly?
No, it's more. We didn't want to change D too much because in many ways that would be making the problem easier. That's a good question. Yeah, we could. Changing D basically means change the environment to make it easier until it works.
Well, that's just the compromise.
Yeah.
How fast your flight platform can fly, or how tight your flight platform can turn.
Perhaps.
And one way to increase the D is get bigger trees.
Yes. Yeah, get bigger trees or something like that. No, we just basically we just wanted to get it to work in a certain environment, and there were all sorts of different directions, all sorts of different things that we could have done to make it better. But basically, lowering R was at that time with a limited time and a limited budget. That was actually the easiest way to do it. And sometimes the most straightforward way to optimize the whole system is not necessarily what is near and dear to you.
Well, my concern is these flight platforms are not always easy to understand how they were designed to work to start with. And screwing with them can be opening up another can of worms. I was impressed with it. Got the flight platform to still work, but you modified it.
Okay. Thank you.
Question. Could you speak
Sure.
to the way you tune the PID controllers, how long it took, and what was the strategy that you followed to tune the PID controllers?
I'm sorry, I couldn't hear you.
The PID controllers based on the optical flow.
Correct.
How did you tune those parameters?
Oh yeah, obviously there's always tuning of parameters. So in practice, what we did is we first got it working in yaw, and then we added heave, and then we added the other parts. But each time you'd start with an initial constant. You'd adjust it until it works, and it took a little bit of trial and error to get the right constants. And sometimes with a different helicopter, you may have to make a slight adjustment to it. So next, I want to tell you about feature creep, and this is sort of there's an unexpected punchline, and it's actually a bitter one in some ways because it kind of relates about how you can go down the wrong path for a few years. Before you wake up and realize what has happened. So what happened is after this demonstration, we is this being recorded for?
Yes, this was on the web.
This is on the web. Okay, so I'll just say that we're going to do a demonstration in an area.
If you want to stop the camera for a while, we can do that too.
Up to you.
I'll just leave it like this. So we were supposed to make an airplane fly down the tunnel, and the demonstration was a flop. It was a very embarrassing failure. We screwed up. We did things wrong. Basically, what happened is we didn't realize that when you pre-build an airplane and stick it inside of luggage and stick it inside of a real airplane, that when it gets to negative 40 degrees centigrade, that balsa wood warps. I didn't know that. Now I know that. But anyway, as a result of that, we were basically told, you know, we like your technology, but we don't want you to fly airplanes anymore. Stay away from airplanes. You make the sensors and let these other people, let another group of people fly the airplanes, fly it. And so we were basically banned from flying for a couple of years. So we did the best we could. We take a look here, and this is sort of a, you know, this is like the features of this particular chip. Photoreceptors, feature detectors, and binarization. Just, you know, there are 3 layers of features. Later on, we added a 4th layer of features. And I don't know how I am on time. And actually, in this case, we showed that, look, we can stick these on a car, drive it down the tunnel, you know, equalize the optical flow on the left and the right sides, and it makes it down the tunnel. And we even made a more complicated version. Look at this. This has 5 layers, programmable biases, multimode I/O. We even stuck a SIMD processor, basically a very simple parallel processor designed to do one thing and measure optical flow. All that stuff on there. We never flew it. We even built this awesome soccer ball thing. You know, a bunch of cameras looking in different directions. And each one would measure optical flow and take an image. And the idea was that each camera could process optical flow at a very high frame rate, I think around 300 hertz, and send back just the optical flow to a central unit. That way you don't have to send all this data back to a central processor, and you basically get rid of the big data problem, shuffling all those bits around. And it worked. People loved it. What happened is then we had a different program manager, because what happens at DARPA is after a couple of years, people forget because you get new program managers. And so the new program manager said, well, we want you to fly. Have you considered flying? I said, you know, that's a great idea. Well, it worked, right? This is what happened. Everything was fine. It worked. See, here's 2 little things, 2 little videos. It's you know, avoiding you know, try to fly to a bookcase that flies away, and the top is hovering in place. Everything was fine. No, it wasn't. That's not what happened. What happened is, okay, we were given permission to finally fly. We had a ray tracing model, and basically we used a computer to generate, basically ray trace a virtual environment. And we first stuck in basically a simulation of the sensors in a simulated environment to see if it would work, how it would work. And you know what? It didn't work. Usually in robotics, it works in the simulation and it doesn't work once you get into the real world. So if it doesn't work in the simulation, you're basically screwed. So and this was about 2 months before we had a major review. And if you've done a lot of work for DARPA in the Air Force, you realize that you live or die by these reviews. You know, someone does this or does that. That's kind of what happens. And we didn't want this. So literally, what I did with 8 of a bottle of wine.
A bottle of wine.
Close to a bottle. Something like that. It was a good wine. It got better. Anyway, I made a list. I made a list of all the features I could think of from past demonstrations that worked. You know, things that could have helped out. You know, was it the optical flow algorithm? Was it the optics? Was it the number of pixels? Was it any of these features on the chips? And I decided, okay, what if I were just to take one of these, or maybe a few of these? Which one of these features actually mattered? If I could take 1 or 2 of these and not use any of the other features, which would matter? And what I realized is that the most important feature was the number of pixels. Don't use any more pixels than necessary. Second most important, a high enough frame rate to control the helicopter or the airplane. That's pretty obvious. And maybe, you know, some little adjustments. All this stuff, all these, you know, bio-inspired stuff, whatever analog processing we had on the chip, all that other stuff that I spent so much time optimizing, that didn't matter. It didn't matter. So here's how we got that demonstration to work. I just got rid of all this, and I used a DSP to emulate a lower resolution sensor, and we got it working in a month. It's brutal minimalism. and it's kind of bitter. But it's a good lesson to have learned, because hopefully I won't make that mistake again. Hope. But again, the lesson is don't use more pixels than necessary. But another lesson is, you see, for a couple of years, we were optimizing these sensors without actually flying them. So the figures of merit that we were using to optimize them were meaningless, because we didn't have the real-world test of a flight test. We didn't have the real-world flight test to tell us if what we were doing actually mattered or not. And that's an interesting lesson to learn. So you know, if you're going to be working on, if you spend too much time working on one piece of hardware, make sure you don't forget about how it's going to play in with the rest of the system, and make sure that whatever metrics that you're using, or figures of merit, specifications, what have you, to optimize it, make sure that those are tuned to your overall goal, not to something that looks good on paper, like number of pixels or this or that. So that's an interesting lesson. Does everyone get that? So it's actually after that we were then able to do this. That work is what led to this. In terms of getting smaller, I'm just throwing in some. Gosh, it's already about. Do you want me to continue on, or should I?
Yes, but
Okay. Okay, a few more minutes here. So basically, how can we get much smaller? We're actually working on a project right now with Harvard University to build a robotic bee, and this is a fun little trick we came up with. Is that you can print up a photo mask. Basically, the same type of photo mask used to make circuit boards. You can print up little pinholes, basically opaque surface with little pinholes. Cut out those pinholes, glue them right onto the chip, and because the index of refraction of plastic is greater than that of air, your whole hemisphere is compressed into a little light cone. And it's a very simple pinhole camera, but it gives you a near hemisphere visual field. And again, if you don't need to use very many pixels, this works perfectly. So we were actually able to, using that, we showed here that we could use just, you know, fly around a helicopter using just this little camera part here, which is about the size of, basically the size of one of these. Just one of these, plus a microcontroller is what we could use to control the helicopter. So we're pretty excited about that. So I mean, I think this is perfect for toy application actually, because the printed optics are so really cheap to print up. And just for fun, not that it's practical. We just want to see if we could do it. We actually made a little Arduino. I call it an Arduino. Basically, it's an Arduino clone with one of our chips on it. In this case, 2 chips back to back. Using printed optics, we're actually able to get a near omnidirectional field of view. And if you move the board around, it was able to give you 6 degrees of freedom of motion measurement, 3 degrees rotation, 3 degrees of translation, purely visually. And we fit that into about 350 milligrams. So it's not practical, but it was fun. I wanted to see if we could make the lightest Arduino. I don't know if we have, but we certainly got pretty close. So that's pretty much my talk. But lessons here is that if you can smartly use a vertically integrated approach and design across different layers of your processing chain, you can realize benefits of one, maybe several orders of magnitude. You can also be minimalist if you're smart about that. And for a few people that are in robotics, try considering ways of measuring the visual field that do not rely upon Cartesian types of coordinate systems. That's probably a bit esoteric, but we've shown here. I mean, this helicopter, it doesn't know its state. So we prove it. You don't need to know the state of the helicopter in order to control it. And I'll stop there. But I will leave you with one quote, actually 3 quotes, but I love this one from Colin Chapman. Because us engineers, we want to add more pixels, add more CPU cycles. Colin Chapman, founder of Lotus Automobiles, adding power makes you faster on the straights. Subtracting weight makes you faster everywhere. Thank you.
A little bit about this before, but a lot of these folks never dealt with working for a government customer. Can you just talk a little bit about like what that was like, some of the lessons learned from people that are interested in pursuing that as a way of funding their technology?
Well, absolutely. So in terms of SBIRs or
Your
So
choice.
most people
Yeah.
here don't know what the SBIR is.
Okay. Okay. I mean, okay. The SBIR program is actually it's a good program, and it's designed for small companies. And basically, what happens is every so often there are basically topics that are put out by government officials, and what you do is you can bid against the contract, and you get and it's basically it's not a grant. It's technically it's a contract to do R&D. Phase 1 is $100,000. I think it's $150,000 in 6 months now to do basically a feasibility study. And phase 2 is $1 million over 2 years to actually build it. And that's a special thing set aside for small companies. The idea is that you have a small company could do it for $1 million. You give it to a big prime contractor. I won't name any names, but they might spend $10 million and not make it work. Just because they have a different mindset, perhaps. So pros and cons in general of working for the government. There are some pros. It's basically you get this R&D money to develop something. You don't have to give up equity. That's great. I mean, who would love to have $1 million and not have to give up equity? Everyone would like that. Other pros are, in the case of SBIRs, technically, if you get one of those contracts and the government wants to buy it, they have to actually buy it from you if you advance to phase 2, because it technically becomes an acquisition, which in theory is great. Advantage number 3, you keep the IP. The government has a license to use it, which means that the government can give it to Lockheed, and Lockheed can build it for government use, but you keep it for whatever else you want to do. That's good. Disadvantages. Doing work for the government requires a more stringent type of cost accounting. Your accountants will become a big part of your expense because you have to. Typically, you're given cost plus fixed fee contracts, and so there's all these esoteric rules that you have to follow in order to just have everything. I'll just say to have it just right. So that means that you need to really have an accountant that is familiar with that. But it also has some limits on how you can spend your money. So, for example, things that are allowable for tax purposes are not allowable for a government contract, like buying booze, or advertising, for example, or PR. That's not an allowable expense for a government contract. You do have a small fixed fee portion that you can use wherever you want. The idea is that that's a fixed profit you can spend any way you want, and that would cover that portion. But that's a disadvantage, probably a major disadvantage. Another disadvantage is
ITAR.
yes, ITAR can be a very big disadvantage.
Can you decrypt some of these?
Pardon?
Just spell out these acronyms.
ITAR, International Traffic and Arms Regulations. So technically, your stuff might be considered a munition, which basically puts it under the same category as a guided missile or a nuclear bomb or a rifle. And what that means is that one, you cannot hire foreigners to work on it. 2, you cannot hire a foreign company to work on it. Forget outsourcing PCB production to China. And 3, if you want to sell it, you have to be very careful that it does not get in the hands of the wrong person unless you get the proper licenses. Otherwise, you have very big penalties. And so that can be a challenge and perhaps a headache. But not all contracts have those clauses. But it can be a potential minefield because people go to jail for that type of thing, and no one wants to do that. I'm willing to risk bankruptcy. I'm not willing to risk going to jail. I have a 1-year-old.
Can you also take angel or VC money?
Yes, you can. And in fact,
Playing rules of-
absolutely, yes, you can. And a lot of people do that. And I think that's actually a great way to we haven't done that, but other people have. And I think it's a great combination because you can then use the government side to develop the technology, basically eliminate that risk, and use the angel and VC money for all of your marketing expenses, to handle marketing or all these other things that are allowable for tax purposes, but not allowable for the government cost accounting purposes. In our case, one thing that we're actually trying is I've become very intrigued by the lean startup methodology, and of course, government and lean don't, But for example, we're completing a phase 1 with the Navy, and what we're actually doing is we have a small sort of a private crowdfunding round with a few people where they're actually paying us to build some of the hardware that we're ultimately going to build in phase 2, but let's go ahead and build it in phase 1 and get it in their hands so they can give us feedback. That way, when we go on to phase 2, we're more likely to have something that people would want to use, as an example. So I think there's a lot of interesting possibilities there. But that's kind of the strengths and weaknesses of the two. Another advantage of government contracting is you can often get a chance to network with prime contractors who could potentially become customers. Many times, Lockheed, Boeing, etc., when they do a major thing, they want to bring in small companies because, one, they have to, and two, because small companies can basically bring in an expertise that they simply don't have. But it's a very different type of world and it's a world that probably would seem very alien to a typical, say, angel or VC funded company, especially out here in the valley, in Silicon Valley.
Question. Difference between SBIR and DARPA, or are you commingling the two contracts?
Okay. SBIR is a type of contract. So you can do SBIRs with DARPA, with the Air Force, with National Science Foundation, Department of Energy. The law is that I think it's 2% of all government R&D money has to go into the SBIR program. DARPA is just one agency that has done this. We've been funded by DARPA and the Air Force. More recently, we've done some work for the Navy, and we also been doing subcontract work for several different universities, including Berkeley and Harvard. All that is through government type of projects.
Have any of them made it to phase 3, or are they just phase 1 and phase 2?
Well, it's interesting. And phase 3 basically is commercialization. So any manner in which you sell it, or so basically if you get any money, whether a customer or an investor, and the customer could be a different government customer, it could be a private company. Any type of commercialization is considered phase 3, and it's very unstructured. But what they've noticed is that there is this valley of death, they call it. We here call it the chasm, between phase 2 and phase 3. A lot of technologies get developed very nicely into phase 2, but then nothing happens beyond that. And so there are pilot programs, they call it phase 2.5, where, okay, this is a very promising technology, and one of the main prime contractors is interested in it. We can put some money in to help make that happen, and it serves as a way to let the prime contractors drive that aspect a bit more. I think I'm going to guess that maybe typically you're on your own. Is really what happens, in spite of everyone's best intentions. But I guess if you know that from the onset, you can be smarter and handle that. I'll admit on my side that we've been more of a technology company. I've been operating mostly as almost like a professor without a university, or a professor unconfined by a university. And that results in developing a technology, but doesn't necessarily result in a product that solves a problem. And what I mean by problem, you see, in an academic setting, a problem is not too far from a problem set. Solve this equation, or make a robot climb stairs, make an airplane that flies along a line. And that's a very different type of problem. Making a robot fly above a line is different from, I own a pipeline and there are people tapping money off the pipeline. How do I figure out where the people are tapping? The latter one is a capital P problem. So there's sort of that. A lot of people doing these types of contracts, me included, have not necessarily been very good at going after the capital P problems. Is that a fair statement? It's an honest statement. I think that lean startup methodologies, for example, get out of the building, Steve Blank. I think those are needed. Those are desperately needed concepts for government contracting. That's my opinion.
You mentioned operating as a sort of a professor, and I wonder if this is on a personal level, not a business level, not a government contract level, but on the personal level, this is what you want to do rather than solve what you call capital P commercial business problems. If this is really where you want to stay instead of becoming a big businessman. This question is relevant to a lot of entrepreneurs that I meet here in the Valley.
Yes.
I ask them, what do you want to do when you grow up? Do you want to be, the CEO of Google? What do you want to do? And a lot of people, especially the younger people who come here, don't always have an answer to that. So I'm curious, in your case, how do you feel about that?
Well, the truth is, I enjoy, personally, I do enjoy making things like this and running projects that make things like this and seeing these things work. And I enjoy it when other people enjoy it. But the truth is, eventually you get to a stage you realize, you want other people to buy it. You want because if other people are buying it, that's another measure of whether you're actually generating any value or not. Perhaps maybe that's not the ultimate measure, but that is one strong measure. So from a personal perspective, really I like to do both. But I've come from an academic environment. Well, this is all going on the internet, isn't it? I've come from almost a quasi-academic environment, and personally, it took me a long time to appreciate the difference between the lowercase p problem and the capital P problem. Actually, that brings up perhaps another disadvantage with government contracts, and it's something you have to watch out for. Is that the people managing, oh gosh, this is going on the internet too. The people managing the contracts, they have every best intention for you to succeed. They want you to succeed, and they're smart, and very often they work very hard. Government workers often have the stereotype of being lazy. No, these people, especially at DARPA, those people work hard. They really work hard. But the truth is that they are probably most likely several layers away from the people actually solving the problems. Steve Blank get out of the building? No, they're definitely not out of the building. I'll tell you a story. I actually reached out online to. I was just curious. I reached out online to some people. I won't say where or anything like that because they would be mad at me. And these are people that have experience in Iraq and Afghanistan doing combat supported by drones. And I asked them, okay, what is your number one complaint? What is your number one problem? What completely pisses you off, pardon my language, about drones? And near unanimous, they said, what we hate are that we're doing an operation, and in comes this drone and announces our presence, and the operation is compromised, with often very drastic results. I leave that to your imagination. Meanwhile, the drone operators apparently love the fact that they're noisy. It's seen as a power play. We're noisy, we're loud, we scare people away, we do our job. That's a disconnect. That's a big capital P problem. And I love the metaphor "find the pain," and as a way to pick out an idea for a business, solve the pain. Good. For these people, a pain is not you have to spend 10 minutes filling out a form. For these people, the pain is very bad. It's the ultimate pain. It's just. I guess I'm rambling on, but I think one disadvantage is that there's a bit too much of that type of disconnect and inefficiency between the problem and the solution. That's one other. What was the original question? I'm sorry. This is on the internet.
Another
Please.
question. If you can talk about the DC hardware meetup, and how things. I understand you run a similar thing.
Yes, no, we just started up. So actually, I mean, this is actually how I was introduced to you. I was searching for. I mean, I was very interested in learning about lean startups and just reaching out and connecting with entrepreneurs to try to see what else was going on outside of the government contracting world, and it was very educational. But I found no one interested in hardware, so that's why I basically found you through a Google search. And connected with Nick Pinkerton, who runs the San Francisco hardware startup. And it turned out that actually around the same time I was starting the DC one, there was another one that formed in New York City, and another one that formed in Toronto. So we've actually had just one meetup so far. We had a whopping 8 people show up, and I don't know why that's the case. I mean, some people said that it actually apparently collided with a major hackerspaces group meeting. I didn't realize that. I thought I searched for it, but maybe that's what happened. But we kind of decided that our format is going to be more of a salon format. Basically, get together at a bar, drink beer, and talk about a particular topic. And some people drove about 4 hours to actually attend the meetup. I was pretty honored.
Well, if I went to the San Francisco meetup, that would be about what I have to drive.
I guess so. How long does it take nowadays?
About that.
In 2000, totally off topic. In 2001, I drove from Berkeley at 5 p.m. and made it to Stanford at 6 p.m. So the time it takes to make that trip during rush hour is a measure of the economy.
Yeah.
It's probably a lot more now. Anyway, sorry, that's off track. You can delete that if you want. Anyway, any other questions?
So how would it be different, SBIR to a challenge type of thing? Like say there was a DARPA challenge to fly the insect cross country.
Well, typically, a DARPA challenge is an interesting thing, but the thing about a DARPA challenge is that you don't get paid to play. You only get paid if you win. And so, basically, it's a way to motivate people. If people have other resources, it's a great way to do it. That's a possibility. It motivates people because I think the people that won the grand challenge were motivated more by the fame and the prestige than by the mere $1 million check, $2 million check. But that would be the main difference. People like me would not necessarily be motivated to participate in something like that because, some of our stuff is so risky we don't know if it's going to work. So I don't want to put in, a lot of money and not have it work and not get paid for it. Or I'd like to avoid that. But that's probably the main difference.
Are you at liberty to talk about your future, or have people come to you and given you ideas for the future?
We can talk about that offline.
Okay.
So you were mentioning the gulf between phase 2 and phase 3. So
correct.
On the East Coast, I'm interested in the kind of investor, angel, whatever kind of community that's there, since that's kind of ground zero for all the SBIR and all the government stuff. Mm-hmm. So what's out there?
There is stuff out there, and what's interesting is that some of the venture capital firms are actually they actually know people within the government. So there actually are connections that are made that way. It was interesting. One of the people that sat in on the one of our kickoff meetings for the Navy project. They were all government people, but one of them was friends with a prominent venture capitalist in Washington D.C. So it certainly exists. And actually, there's also InQtel. That's the CIA's venture capital firm. It certainly exists, and I think that in the East Coast, there are more people that are willing to work with government contractor types. I personally have not gone after any investor funds, so I know a few people, but I don't know much about them. I know that it exists, and it exists quite a lot. And sometimes even a prime contractor will. Sometimes there could be effectively institutional venture capital, not from a venture capital firm, but from a corporation. I forgot what the term was, but you understand what I mean.
I think that's going to be the last question. Unless there's one more last question. All right, Geoffrey, thank you so much. What we usually like to do, if you haven't done it already, ready, I usually make this rule of saying, make sure that you've met 2 people you didn't know coming in here. There's an incredible group of people in this room. There always is, and you'll be surprised. Like you might find your next engineer, you can find your next marketing person. Thank you all for coming.
Thank you guys.
How's it going? Great, great. Found a partner and we're working hard to build a new design.
Okay. So what's the big?
Very promising.
Paperclip holds the ring on and it happens
Surprising
just the right way to balance it out. So we never change it.
The folding.
So tell me about
Very small, a lot smaller.
So tell me about the
Smaller ways in the
Yes, they are. I mean, basically, you can get the cartridge. Like I dig on the model number, and basically, you basically make a stencil and you scrape it on and you cure it using heat. Or we actually, in this case, the company that made the boards, they made the boards and they sent it to a firm that specializes in that. Yeah, but that was probably the most troublesome aspect. So actually, one of the things we're doing is we're moving to a quad.
Right.
Just so that